The learning outcomes. So P3.1a, describe that charge is a property of all matter and that there are positive and negative charges. P3.1b, describe the production of static electricity and sparking by rubbing surfaces and evidence that charged objects exert forces of attraction or repulsion on one another when not in contact. Hold on, does that make sense? Evidence that charged objects exert forces of attraction or repulsion on one another when not in contact. P3.1c, explain how transfer of electrons between objects can explain the phenomena of static electricity. P3.1d, explain the concept of an electric field and how it helps to explain the phenomena of static electricity. P3.1e, recall that current is a flow of charge, electrons, and the conditions needed for charge to flow. Static electricity. Let's talk about what causes the effects of static electricity. Now, what happens when you rub two objects together? So I'm going to draw a diagram of like two objects rubbing together. So here you've got two objects rubbing together in opposite directions, and friction is the opposing force of motion. So whenever you have opposing forces, a frictional force, there is a frictional force. Now, imagine if we zoom into a part of where the two objects meet. Now, in actual fact, when you zoom in, you get these imperfections. So it's not perfectly smooth. So here you get these imperfections. So if you were to zoom in, you'll get these imperfections. Now, if you zoom even closer, you might get like these tiny valleys. You might get these bumps. And here you might get these. So if you were to zoom in, even further, you'll get these mountains, let's just say. So here are these mountains. The correct term will be called asperities, where you get these high and low valleys. So if you were to rub these two things together, so let's just say that's going in that direction and that's going in this direction. When you have friction, so when there is friction, you affect the electrons. So the electrons are affected. So here you have these electrons, they are affected. For this diagram, you've got an atom, you've got a nucleus, and you've got the electron cloud. So this is not the Bohr model. This is the Schrodinger's model. This is the quantum model, where you've got probability of electrons. So here, have a look. So here you've got the electron clouds of one object and the electron clouds on the other object. So this is on the boundary, this is on the surface of those objects. And what happens when you bring them closer together and then moving in the opposite directions? The electron clouds overlap with the electron clouds in the other object. So here you can see that the electron clouds can overlap with the electron cloud of the other object. Now this diagram here, the one on the left, it looks like you've got two rectangular objects that are moving in opposite directions to each other, and because of this friction, the electrons get transferred from one object to the other. Now if you look at it close up, if you were to zoom in, they won't be perfectly smooth, it'll be rough. So look at the mountains in the blue objects, the one at the top, and the red objects at the bottom. the red object at the bottom. So you can see that both objects are not smooth, but you get bumps. Now when you rub the two objects in opposite directions, the electron cloud in those atoms will overlap the electron clouds in the other object, and you get repulsion, you get attraction. So therefore the electrons will move from one object to the other, they get repelled. So when you have two objects rubbing against each other in opposite directions, the electrons get transferred from one object to the other. Because the electron clouds in one object overlaps with the electron cloud in the other, there will be asymmetric electron cloud distribution. You end up with a voltage, meaning because you have an uneven distribution of charges, you get one side more positive, one side more negative, you get energy, you get a voltage, you get an electric field. Because if one side is negative, one side is positive, you have an electric field. And whenever you have an electric field, you set up a voltage, you set up kind of energy, and that energy can move the electrons from one object to the other. The key word is asperities. So these are like tiny mountains on objects. So what does it mean? So these are high spots on surfaces that come in contact during friction or wear and tear. The forms, shapes and deformational characteristics of these asperities play a role in modeling tribo contacts. Can you see that the cursor's there after modeling? I just screenshot the picture. Especially in cases where liquid lubricating films are either absent or so thin that solid to solid interactions occur. So these asperities are these lumps and bumps, high spots on the surface. Yes, and in the video I have said it incorrectly. I may have said it incorrectly. Okay, so how are these electrons affected? Now let's just draw the atom and the electrons around the atom. So so here's the nucleus, here you got these electrons. Now we're going to use the wave model. So the wave model, where is a cloud of electrons. Now normally it is symmetrical. However, if you were to rub, so let's just say you're rubbing in this direction, the cloud will be asymmetric. So now the cloud, so it could, this is just my thinking, I'm not 100% sure, but it becomes asymmetric. So because before you are rubbing the materials together, the cloud of electrons are normally symmetrical. However, when you rub them together, when you rub two materials together, insulators together, the cloud of the electrons will move and it will become asymmetric. If you were to compare a conductor, let's just say, so this is a conductor, and here you will have free electrons. So here you have delocalized electrons, and these will be freely moving, so freely moving. But because in an insulator the electrons are trapped, the electrons are not freely moving. The cloud of the electrons, they can only become asymmetric. However, for a conductor, because the atoms are delocalized, they're freely moving, then static electricity is very difficult to occur. Alright, so what happens when you have an asymmetric distribution of charge? So if you look at the top diagram, So here you've got a positive charge, and here you have a negative charge. Because the charges are separated, you're going to end up with a voltage, or you can say there's an electric field. So the electric field would, now if you imagine a positive test charge, where would the positive go? It would repel from the positive, attract to the negative. So the field would go in this direction. So if you have a asymmetric distribution of charge, you will have an electric field. You end up with a voltage. Now this voltage, how does this explain static electricity? Alright, so static electricity is actually quite hard to explain, but let me just read an article that I copy and pasted from Live Science. Mizzi and his colleagues discovered that static electricity is produced when the asperities in insulators rub against each other and interfere with the electron clouds. Since the electrons in insulators can't move around easily, that rubbing can bend the electron clouds out of shape. In those materials, the cloud of electrons around atoms is usually symmetrical. When you look at these clouds, you can't tell up from down, left from right. But if you squeeze that electron cloud, it deforms, becoming asymmetrical. Under the right circumstances, that new shape can distribute voltage unevenly across the material. What does this have to do with wool socks on carpet? As you walk in such footwear, the combination of your body's weight and your striding motion causes the fibers in your socks to slide against the fibers in the carpet. When the two materials rub against each other like this, the bumps on one surface drag along the asperities, meaning bumps on the surface of the material, on the opposing surface, causing them to bend. When this bending happens, the electron clouds in the atoms that make up the asperities get squished into asymmetrical shapes, causing a very, very small difference in voltage. However, these voltages add up. Asperities are so numerous that the squishing of electron clouds causes a significant buildup of static electricity, one powerful enough for you to feel it when you touch a doorknob or shake someone's hand. Okay, so the question is, what is charge? What is charge? Now, we can't say what it actually is, but we can say that charge is a property of matter. So in an atom, you've got the positive nucleus and you've got the negative electrons orbiting the nucleus. So you have the positive nucleus and you have the negative electrons. So here you have the positive nucleus and you have the negative electrons. So what is charge? Well, we don't know, but we can say it is a property of matter. So the question is, what is electric charge? Now, an electron has a charge of -1 and the charge of a proton is +1. However, I mean, so far we think that the electron is fundamental, meaning that nothing makes up an electron. However, what are inside protons? Now, inside protons you have 3 quarks. Now, if the charge of the proton is +1 and there are quarks inside the proton, that means the quarks must have a fractional charge. So an interesting question would be, where does the electron get its charge from and where does the quark get its charge from? Alright, I mean, it is a university level question. What is electric charge? However, electric charge is a measure of the strength of a particle's interaction with the electromagnetic field. Now, when you accelerate a charge, it will give off electromagnetic radiation, and photons can exert electrical and magnetic forces on charged particles and magnetic particles. Particles do not obtain a charge from the field. So if you say that a particle has a charge, it's the same thing as saying when it interacts with an electromagnetic field, it has a certain strength. So for example, we called the electron negative. It was just arbitrary. It was just by convention. We could have called the electron positive, but we just happened to name it negative. So the electron is negatively charged. Let's just say it's -1, and then we compare the charge of all the other particles with the electron. Next, we're going to be talking about electric fields. So what is an electric field? Alright, so if we have a positive charge and a negative charge, what would happen if you put something that's charged near this object? Now, I'll tell you, to draw the field, what would happen if you were to put a positive test charge here? It would repel from the positive. So the field line would go like this. Now, because it is attractive, this would be curved. So still go like this. So if you were to put a positive test charge, it would be repelled from the positive charge and it would go to the negative charge. Here, if you were to put positive charge there, it would go to the negative because it would be attractive. So imagine a positive test charge. And it's always going from positive to negative. Electric field. Electric field is defined as the electric force per unit charge. The direction of the field is taken to be the direction of the force it would exert on a positive test charge. The electric field is radially outward from a positive charge and radially in toward a negative point charge. So if you were in an electric field, and if you were positively charged or negatively charged, you would experience a force. So an electric field is a region of space where if you were to put a positive charge or negative charge, it would experience a force. If it was neutral, then it may experience a force as well, depending on how it cancels out. And what about current? What is current? I'm going to show you the equation first. Okay, so the current is how much charge passes through a point per unit time. So supposing that this is point A, so can you see that in scenario 2 it has more current because the electrons are more. So there are more electrons passing through the point A per second, assuming it's the same time. Now the symbol for current is I. The symbol for charge is Q. The symbol for time is T. So I is equal to Q divided by T. That is measured in amps. This is measured in seconds. And this is measured in coulombs. When a polythene rod is rubbed with a duster, the friction causes electrons to gain energy. Now, if you remember the asperities, the mountains and the valleys and the troughs, because when you zoom into an object, it's not perfectly smooth. You're going to end up with bumps in the object. So when you apply friction to the objects, when one goes in the opposite direction to the other, the electron clouds will merge, and you could end up with a brief ionic bond or brief covalent bond. And so when that happens, you're going to end up with an asymmetric distribution of charge, and you end up with a voltage, and this is where the electrons gain energy. And so when electrons gain enough energy to leave the atom, this is the second sentence now, when the electrons gain enough energy to leave the atom and roll off onto the polythene rod. So now the polythene rod has gained electrons, giving it a negative charge. Now you need to remember that only electrons can move, because you can't move the protons and the neutrons. You need a lot of energy to separate the neutrons from the protons. And the duster has lost electrons, giving a positive charge. If the rod is swapped for a different material, such as an acetate rod, electrons are rubbed off the acetate and onto the duster. The acetate rod has lost electrons, giving it a positive charge. The duster has gained electrons, giving it a negative charge. Both the rods and the duster are made of insulating materials. Now, because insulators, they don't have free electrons, they can store charge. However, so let me just carry on reading the second sentence in that paragraph. Insulators prevent the electrons from moving and the charge remains static. Conductors, on the other hand, cannot hold the charge because you've got free electrons, delocalized electrons, as the electrons can move through them. So they don't really store the charge. So if you compare insulators and conductors, insulators will store more charge compared to a conductor. Electrical forces. So if you have a charged object, it will experience a non-contact force. So friction is a contact force because you need the two objects to be rubbing, and that will be a force experienced between those two objects when they oppose each other. However, a non-contact force is when they don't need to be touching. So if you have an electric field, in this case, this will be a non-contact force. So the type of force will depend on the type of charge, positive or negative, on the two objects. The properties of attraction and repulsion are often used to show an object is charged. Now, a charged rod can pick up small pieces of paper. All right, so small pieces of paper are normally neutral; they are not charged. But inside that piece of paper, you still have electrons, and inside those, atoms. And inside that paper, you've got atoms, and inside those atoms, you've got positive protons and neutral neutrons, and you have negative electrons. But overall, the charge is zero. But you still end up with, but you still have charges in them. But if you have a charged rod, that charged rod can affect the charges inside that neutral piece of paper, and it can still move. A charged balloon can stick to a wall by attraction, and a charged rod can pull a stream of water towards it. Now let's have a look at the top right. So here you've got a polythene rod and a duster. So the polythene rod, how many negative charges do you have? You've got 4, and you've got 4 positive charges. So overall it's neutral. And the duster, I assume, is the same number of charges, positive and negative. Yep, you've got 5 there. This is before rubbing. And then after rubbing, what happens is that the electrons get transferred to the polythene rod. So now if you look at the electrons in the polythene rod, you get 1, 2, 3, 4, 5, 6, 7 negatives and 4 positives, and you've got 5 positives and 2 negatives in the duster. So this is after the rubbing. So now you have an electric field. So the one that is more positive and the one that's more negative, because you've got a separation between the two charges, you have an electric field, and whenever you have an electric field, you have a force in between them. Let's look at the duster and the cellulose acetate. So now the cellulose acetate will be neutral, and the duster will also be neutral. And then when you apply friction to both objects, the electrons will move from the cellulose acetate into the duster, meaning that the electrons will be transferred, and so therefore the duster will be more negative and the cellulose acetate will be more positive. Now, because you have two objects that are now unevenly distributed, you're going to end up with an electric field. So meaning that because the charges are separated, it is no longer neutral. I mean, overall it is neutral, but if you just focus on the individual object, One object is more positive, one object is more negative, so you end up with an electric field, and so therefore when you have an electric field you end up with a force. All right, so now let's look at the bottom right picture. So because the wool is positive, the polythene is negative, you end up with an electric field. So the arrow is pointing towards the left. So meaning that if you were to put a positive test charge, the test charge would go from the positive wool to the polythene rod because it is attracted to the negative rod. So because there is an electric field, there is a force. If a cloth rubs a plastic rod and the cloth is pulled away from the rod slightly, will the rod and cloth attract, repel, or experience no force at all? So the answer is the rod and cloth will attract. This is true as long as there is enough friction to transfer electrons. Now remember, it's only electrons that move. The protons do not move. If electrons are rubbed off the cloth and onto the rod, the cloth will be positively charged and the rod will be negatively charged. So if something has more electrons, it is more negative. If something has less electrons, it will be more positive. So if an object loses electrons, it will be more positive. If electrons are rubbed off the rod and onto the cloth will be negatively charged and the rod will be positively charged. And in both cases, the opposite charges will attract.